synchronize our approaches into a strategy, and then break that back down into our subtasks. And then I'm going to hand you over to John here, who's going to tell you about our progress since last year and what we've been doing and where we hope to go with it. So I'll just bring you up to speed. So this is our bacterial relay race, and our plan is for one group of bacteria to be motile and move up to another one, and then there'll be some sort of signal to the second group of stationary bacteria who will then become motile. So this could be good for a lot of reasons. It could be fun to bet on, and you know, all these restriction digests are taking so long. What do? Well, maybe run a little race. So also, one of the interesting things about this project is with a few modifications, it could be repeatable in units. So instead of just 2 bacteria, we could go to 3, 4, and soon we're having some pretty big projects here. So how are we going to accomplish this? Well, our system has 2 main constraints. First, we need a way to make stationary bacteria motile, and we'll get into that in a second. And the second thing is that we need a way to direct movement. So the race can't just be in some sort of any direction. We have to have a linear path that our bacteria are going to be swimming along. So to control motility, we have this protein called MOTB, which is a proton pump, and it fits into the cytoplasmic membrane, and it's one of the last proteins to be to fit into this flagella. So if we can knock, as Blair and Berg showed, if you can knock it out of this chromosome and put it on a plasmid, then you can express it and get motility restored in about 10 minutes. So it would work very well for our project. So how are we going to accomplish? So now the second thing that we need to do is direct movement. And the solution comes not in chemotaxis for us, but in microchannels. So by having, because of the rotational movement of the flagella, it's spinning, and it's going to add a little bit of torque to the bacteria as they're moving forward. So Whitesides and Berg showed that if you have bacteria swimming straight along the wall, they're going to keep bumping up into the right side. So instead of having some sort of gradient for a chemotaxis, we can just put them in microchannels and they'll swim linearly. So, and this system works even better when we're going to use quorum sensing to have our signal between the 2 bacteria, and this can hopefully raise our concentrations of quorum sensing molecules, so we won't have to, so it'll be a little easier to have a few cells or one cell produce enough molecules to sort of get the second cell started. So here's our strategy. We just have this first cell producing these quorum sensing molecules, and it's moving along our racetrack here. And some of these diffusible molecules are going to move into cell 2 and restore motility. So here our second cells go. And the advantages of this strategy are that, as we've even seen earlier today, other people have used AHL and other quorum sensing molecules to control their systems. But a disadvantage is that our system, because we're using MOTB, just a very small expression of it actually will start the bacteria moving again. So we have to be really worried about leaky expression, or we're going to have premature motility. So here's just our circuit. We have constitutively expressed Lux I producing our quorum sensing molecule, and it's just going to diffuse across the cell membranes here to cell 2, and it's going to bind to the Lux R, which can now bind to the promoter and create Lac I. And this is just going to repress C1, so flipping our switch here. And Lac I is also produced in our switch, so it's a positive feedback loop there. And this is going to, now since C1 was repressing our MOTB, now the repression is lifted, and we can create both MOTB and GFP. So we have the MOTB going down there, the GFP is being expressed, and we're sort of off to the races, if you will. So now we're going to need to fabricate our microchannel. So the first thing that we're going to do is use photolithography to create these small features in a silicon wafer. Then we're going to spin coat a layer of PDMS on and cure that. And now we're going to peel off the PDMS and put it on our iCAN agar. And now some fluid from the iCAN agar is going to drop into these microchannels, and now we're going to have fluid-filled microchannels that the bacteria can swim in. So here's just a picture of our microchannel underneath the microscope on glass. And we're going to use 10 microns as the width of our channel for the bacteria. And here's just a wild-type cell swimming in one of our microchannels, and in just 6 seconds, it's moved 60 microns. So this is a pretty fast-moving race here, and you know we can have a number of even centimeters for the total race. So we're sort of dealing with a pretty large scale for bacteria here. And now I'm just going to pass you off to John, and He's going to tell you what we've been doing this year.
Okay, so the major crux of our project is being able to demonstrate whether or not we can actually repress MOD-B, which was a major question mark at iGEM last year. We've made some progress towards that. So the first system we designed to test whether or not we'd be able to repress MOD-B was the simplest one available to us, and that was to place it under control of a lac promoter, lac-I promoter. And this would allow us hopefully to both repress MOD-B and show induction with IPTG. And there's just a diagram of the construct. But unfortunately, this didn't work out too well. So you can see here that this here is our positive control, which is strain RP437, which we obtained from J.S. Parkinson at the University of Utah. So that's wild type for motility. Here's our minus control, which you can see didn't swim on either plate. And colony 3 down here contains our lac-I inducible construct, and you can see that we're getting premature motility on the cells containing 0 IPTG, which was not a very encouraging result. So we came away from this, we kind of regrouped, and we designed a new system that was more unique to our particular application of the project, and that was placing MOD-B under control of the LuxR promoter. So in this case, we were able, hopefully, to induce motility with HSL, and hopefully address some of the leakiness issues from the P-LuxR promoter, which has been documented in other people's projects. So here's just a diagram of the construct here. We have constitutive LuxR expression and MOD-B under control of the LuxR promoter. Our original MOD-B construct contained an endogenous ribosome binding site, which we thought to be strong, which will kind of come back into play later. So again, we did some swarm assays here, and we got, unfortunately, very similar results, which was also very demotivating. So up here, again, you have our positive control, our minus control, and colony 3. There's actually more swarming on the non-induced plate than there is on the induced plate, which really baffled us. But it led us to believe that even a very little expression of MOD-B was enough to restore motility, and that leakiness from LuxR, which has been documented in other cases, was the culprit for premature transcription and expression of MOD-B. So we regrouped again, and we decided to go back to our original system and see if an additional amount of lac-I would be enough to repress MOD-B. So again, we really needed to be able to show that we could fully repress motility, because the point of the relay race is having a bacteria entirely stationary to accept the signal and then be induced to swim. So we designed this system combinatorially. We weren't sure exactly what type of output was going to be necessary to fully repress MOD-B. So if you multiply those out, that's actually 9 different constructs, which we cloned simultaneously, added a whole bunch of extra problems along the way with cloning, but we were able to clone them all. And you can see here that the constitutive expression, high transcription with a strong ribosome binding site of lac-I, would repress MOD-B back here. And we designed it in such a way that if there were any read-through through this circuit, it would actually work to our advantage and repress MOD-B further. So, hooray, it works, at least partially. So you can see here that, again, we have our positive control and our negative control. And these are a series of constructs with either decreasing ribosome binding site strength or decreasing promoter strength. And you can see here that colonies 3 and 4 worked well because they contained the highest transcription promoter and the highest available ribosome binding sites from the registry. Colonies 5 and 6 contained weaker ribosome binding sites, contained one weaker ribosome binding site, the other one contained a weaker promoter. So you can see that the MOD-B wants to be expressed and will restore motility fairly easily. So we needed to pump out a lot of repressor to fully repress it. So this was encouraging. And we accomplished that task as well. So our next steps here, now that we've shown that we can fully repress MOD-B, that was kind of a proof of concept for us. We could show that we could continue at least working on the project as a whole. So we decided that the best way to address the leakiness out of our LuxR promoter and our HSL input circuit would be to PCR out the endogenous ribosome binding site from our original MOD-B registry part and clone in the 5 available ribosome binding sites from the library, even though that some of the stronger ones probably wouldn't work out too well for us. And this is an ongoing process. I actually just finished cloning this last week, so we haven't had a chance to test them yet, but we're hopeful that knocking down the ribosome binding site strength in front of the MOT-B will help address the leakiness of the LuxArc promoter. So in the process, we've also submitted a new registry partner. Some other progress we've made is we've constructed all of our sender devices, and again, we've taken a combinatorial approach to this as well, because we're not exactly sure what type of output is necessary to induce motility in the recipient. We're not sure how sensitive it's going to be. So we've designed a system with a series of promoter strengths, ribosome binding site strengths, and both tagged and untagged versions of Luxi protein generator to see, so that hopefully once we nail down the motility problem in our receiver, we'll have a library of sender cells from which we can choose the best one. So some challenges we faced along the way, and there were many, as it seems everybody faces. We often took a combinatorial approach to cloning because a lot of the parts we've been using in our system have been poorly characterized, at least in a biobrick sense, especially the MOT-B. We learned kind of the hard way that it's very sensitive to low transcription, and it will restore motility even at a low expression rate. We've had some difficulty demonstrating impression of MOT-B under control of P-LuxR, which I've shown, and we're still not sure exactly to what degree the ribosome binding site must be reduced to address that leakiness problem. We still have yet to determine the exact level of HSL necessary to induce motility in our recipient. And another problem for further down the line is visualizing this interaction actually in our microchannels and figuring out a way to place our receiver cell in the microchannel so that it can receive the signal from the sender. So just some future work that we have that we'd like to accomplish in the near future. Again, cloning a library of MOT-B with varying ribosome binding site strengths and then testing for repression and induction with HSL. We also want to examine the possibility of using antisense RNA and riboregulators as a possibility for addressing this leaky P-LuxR problem. And then, hoping that works, we'd like to plate the sender and receiver cells together and see if we can show an interaction where the sender cells are inducing motility in the recipient just on a plate without a microchannel separating them. And then, if that works, separate them with a microchannel. Again, visualize the interaction in the microchannel. We need to do some more strain construction and knock out lac in our MOT-B defective strain so that we can test our switches. And we're also thinking about implementing a bicellular communication device that will feed back to the sender cell and tell it to stop swimming after it has emitted a signal to the receiver to start swimming so that we can actually get a full relay race effect. So we'd just like to thank all the sponsors and our faculty advisors for providing guidance and open up to questions.
Thank you very much. Got about 10 minutes for questions. Anybody have questions? Do you guys have a favorite part that you really liked, and why'd you like it?
We obviously like our MOT-B because that's kind of the crux of our project, and there's two versions of it. There's one with its endogenous ribosome binding site from last year, and then the one which we just made this year without its ribosome binding site. And those are both in the registry.
Okay.
Over here?
So you said that you
Okay.
have this bacterial relays in microchannels for
Uh-huh.
bacteria swimming around, but all your assays you studied swarming behavior on plate, and actually the two behaviors differ to an extent because swimming is within the pickup and swarming is
Right. Those swarming assays were more not as a proof of concept for the actual motility. It was designed to see whether or not we could actually turn MOT-B off. Because we knew that it was going to be a problem. If we couldn't turn off MOT-B, then we wouldn't have a relay race because all the cells would be swimming all the time. So those assays were just designed to see whether or not we could physically repress MOT-B by putting it on plasma.
Did you have any trying assays in actual microchannels?
We haven't tried it yet, no, because we haven't been able to show repression until recently.
Do you have some way of making the sender stop after it sent its signal and only the receiver to move?
We're thinking about ways that we can do that via bicellular communication mechanism, but that's a little further down the line. We'd like to get some of our core systems working before we do that. That's kind of an icing on the cake thing.
So, did you try tagging your MOT-B with LBA? Is it trying to be very faster?
We hadn't thought of that, but I assume it would be a good possibility. I'm not sure if that will diminish the functionality of the protein at all, since it is embedded in the cytoplasmic membrane. So,
can you talk a little bit about matching the intercellular dynamics of motility and diffusion with, for example, a 4-hour switching time you might have in the autologous, especially in the microfluidic environment?
We're not exactly sure, honestly, how to address that yet. It's been progressing as far as complexity goes throughout, and after we can show that we can repress MOP with our HSL input circuit, then we can start worrying about the dynamics of the switch involved. We were actually able to, Tim Gardner at Boston University was able to provide us with some of his bistable switches so that we won't have to construct them ourselves. So we'll be working on that more after we can characterize the specific interactions with MOP in our project.
And perhaps actually doing away with the switch and using the riboregulators that Berkeley showed was one suggestion that Tim gave us to sort of speed it up.
In your original leaky experiment with the MOC-B, where was the lac I encoded?
It was just basic phenotypic expression. It was in a lac I positive strain.
Questions?
Any other questions? All right, let's thank our speakers. Oh, wait.
Just quick summary. How are you characterizing MOP-B, or as a part, as your part?
Basically through motility assays. So those are iconometer plates, which I think was mentioned during Cambridge's presentation this morning. And that's pretty much it. That's been shown to be a good assay for doing motility type work in some of the literature we've been reading.
Okay, now.